Let's see the basic stiffnesses of member. If we allow unit deflection here, then both ends, just like a sinking of support, fixed end moments developed are 6 EI upon L square, 6 EI upon L square, anti-clockwise if right support sinks down. And therefore reactions are total moment, sum of end moments divided by span becomes 12 EI upon L cube, 12 EI upon L cube, and reactions will form equivalent opposite couple. Moments are anti-clockwise and reactions will form clockwise couple. Similarly, suppose left support goes down, then clockwise moments at both ends developed will be 6 EI upon L square and reactions will form anti-clockwise couple, and each reaction will be 12 EI upon L cube, that is sum of end moment divided by span. Similarly, these are the basic stiffnesses when a sinking occurs. Similarly, if rotation is given, introduced, so the rotation is clockwise, therefore here clockwise moment, fixed end moment developed is 4 EI by L, and further end clockwise moment developed is half of that, 2 EI by L. Similarly, suppose you have a fixed beam here, and if you apply, say, anti-clockwise, here say it is like this. Anyway, if rotation is anti-clockwise, moments are anti-clockwise. If rotation is clockwise, moments will be clockwise. So here I have introduced anti-clockwise moment, means anti-clockwise moment developed, fixed end moment developed here is 4 EI upon L, and further end again anti-clockwise 2 EI upon L. And then knowing this is clockwise reaction, this reaction is downward, this reaction is upward, this is 6 EI upon L square, and this is 6 EI upon L square. Similarly, this is anti-clockwise, the reactions here forms clockwise couple, 6 EI upon L square and 6 EI upon L square. So these are called basic stiffnesses. While solving problem, any problem by using stiffness method, we need only this much, that's all. In order to find out coefficients, stiffness coefficients, so only these basic stiffnesses are required, and that's why the problems are more simpler, more easier. Now let's consider problems one by one. Say already we have solved few problems by using flexibility method. We will try to solve the same problems by using the stiffness method. So let's consider a proper cantilever. We already solved this problem. Say proper cantilever carrying UDL AB. L is the span. It carries load W per meter run. Proper cantilever. We already solved. We know the answers. Now let's solve by using stiffness method. Now here first of all we have to locate the unknowns, and displacements are taken as unknowns, or KDI. What is KDI for this? So A is fixed, B is prop support, only theta B, that is KDI is 1. What is that? That is only theta B. So therefore let assign the coordinate theta B equal to say D1. Means here see, if you draw the deflected shape by a dotted line, it will deflect like this. If you draw the tangent here, so this is theta B. This is unknown. Theta B is unknown. So only we have neglecting axial deformation. We generally neglect axial deformation while solving the problems. The next is, let's assign the coordinate. So this is fixed and this is prop support. Let's take a clockwise D1. Say assign the coordinate. in the direction of unknown. Unknown is a rotation. So let's assign the coordinate. So we will assume clockwise positive. So D1. The next case, obtain restraint. So this is called assign coordinates. Assign coordinates. Now next step is obtain restrain structure. Obtain restrain structure by locking all the joints. So make it fixed. So this becomes a fixed beam carrying UDL. So this is called a restrained structure. This is called a restrained structure. Then say find out the fixed end action. Say this is L. So this anti-clockwise WL square by 12 left hand. Right hand we have WL square by 12 clockwise. So these are the fixed end actions that we know. Now in the direction of D1 we want. So here D1 is clockwise, this is also clockwise, so that is plus. And then remember, so reactions here are not required because D1 is a rotation, corresponding action is a moment. So in the direction of D1, this is AD1L is this, AD1L. So that's over. Next is, let's draw, find out stiffness coefficient. Say this is now fixed. Allow unit rotation here. Allow the rotation clockwise because we are taking clockwise positive. So allow rotation clockwise. When we give the unit rotation here, the fixed end moment developed here is 4EI due to this is upon L. And here this end, this is 2EI upon L. Half of that with same sign. And this is called stiffness coefficient, K11, in the direction of 1 due to 1. There's only one unknown, so this is sufficient. So this is to be multiplied by, these coefficients are to be multiplied by D1 in order to get the final action. Now next, using joint equilibrium equation, we have to now use joint equilibrium equation. That resultant action or moment at B must be 0 because B is a simple support, prop support. So MB must be 0. That means this plus this must be 0. So that means AD1L, only one unknown we have, K11D1 equal to 0. You substitute this. This is WL square by 12, WL square by 12 plus K11 4EI upon L D1 equal to 0. Let's find out D1. So D1 will be, this will be minus on this side. It is WL cube upon 48 EI, but this is minus. So this is D1. So we have calculated D1. D1 is nothing but theta B. D1 is nothing but theta B. Now once we get D1, joint displacement or theta B, now using slope deflection equations, you can find out MAB. So MAB, now using slope deflection equation. What is MAB? MAB 2EI upon L 2 theta A plus theta B plus minus MFAB. That means this is 2EI upon L. This is theta A is 0. and this is minus WL cube upon 48 EI, and this is minus fixed end moments WL square by 12. So now this you can solve. This MAB will be equal to, say this will be, you will get minus, no, this is minus, so minus, and this EI gets cancelled, this 1L, so this becomes square, here you get 24, so WL square by 24 plus WL square by 24, so WL square by 8 you will get, and anti-clockwise, that is hogging. So what moment you get here is, anti-clockwise, negative, that is anti-clockwise, and value is WL square by 8. So we have calculated moment. Now so this is by using slope deflection equation. Instead of going for slope deflection equation, I will tell you very easier thing, that just look at the beam. So this we want to, now MAB, I will write down here directly, MAB, this minus anti-clockwise WL square by 12, and this is clockwise, plus 2EI upon L into D1, so into D1, that's all. So instead of writing down the slope deflection equations, we will find out this way. Now you substitute this, minus WL square by 12 plus 2EI upon L, and this is minus WL cube upon 48 EI. So this gives us again minus WL square by 8. Now here we have calculated fixed end moments. Now next, what is the next step? Next step is to find reaction at B, and then you know how to construct these diagrams. Say knowing the fixed end moments, how you will calculate here RB. So you take summation M about A equal to 0. RB, due to RB it is anti-clockwise, so RB into L. This is also anti-clockwise, plus WL square by 8. And due to load it is clockwise, so minus WL square by 2 equal to 0. So solve this, you will get RB 3WL by 8. You will get RB 3WL by 8. And we know this further because we have solved already. This is 3WL by 8. Now we can construct SFD BFD as usual, and for RA use summation Fy equal to 0, RA plus RB equal to WL. So RA you will get 5WL by 8. So RA will be 5WL by 8. So with these reactions and end moment, you construct SFD and BFD. Now next problem. So one more problem, a systematic problem we will solve. Now say let's consider a continuous beam. So we have solved this problem by using flexibility method. Let us solve the same problem by using stiffness method. Let us solve the same problem by using stiffness method. Now here, what are the first, look, find out kinematic degree of indeterminacy, or we can locate the unknowns. Here it is 2, theta b and theta c, theta b and theta c. So now let theta b equal to d1 and theta c equal to d2. So let theta be equal to d1 and theta c equal to d2. Next, let's assign the coordinates. Let's assign the coordinates. Say this is fixed, simple support, simple support. So in the direction of theta b, d1, in the direction of theta c, d2. So assign the coordinates. Simple, very simple. Next, obtain the restrained structure. So by locking all the joints, fix all the joints. Then show loading on it. And find out restrain reactions, means fixed end moments. Let's find out, because these are the rotations, only our interest is fixed end moments, no reactions. Say this, we know this is WL square by 12. So 12 gets cancelled, so this is 16. And here also you will get 16. Then here anti-clockwise, here clockwise, this is WL by 8 central load, WL by 8. L is 4 to 30. So this will be 30 and this will be 30. Then these are the restrain reactions. Now in the direction of D1, this is AD1L equal to, this is clockwise, this is minus, so you will get minus 40. And this is in the direction of AD2L, this is clockwise, therefore plus 30. So AD1L and AD2L we get. Next, stiffness coefficients. So very simple stiffness method. So just apply the unit, we know the basic stiffnesses of the member due to unit rotation. Now here D1, in the direction of D1, if we give the unit rotation in a clockwise direction, so this will be rotated. So if you draw the tangent here and tangent here, say this is 1, this is 1. So when we introduce the unit rotation at B, then clockwise movement here will be developed. This is 4 EI upon L is 4. This is also 4 EI upon L is 4. So this 4 gets cancelled. So here it becomes EI by 2 clockwise, and here also clockwise EI by 2. EI by 2, EI by 2. Then this is in the direction of 1 due to 1, K11 EI plus EI, so it becomes 2 EI. 2 EI. This is in the direction of 2 due to 1, so EI by 2. The next, apply the unit, say keep it fixed, and unit rotation here is applied in a clockwise direction. If you draw the tangent, this is 1. So clockwise moment developed here is 4 EI upon L is again 4, and here clockwise moment is EI by 2. So that means this is in the direction of 1 due to 2 clockwise, this is in the direction of 2 due to 2. These are to be multiplied by D1 and these are to be multiplied by D2. for final actions. So now the problem is almost over. Simply write down the equilibrium equations and solve for d1 and d2. So using equilibrium conditions, AD1L plus K11D1 plus K12D2 equal to 0. So this AD1L is minus 40, K11 this is plus 2EID1 and this is plus EI by 2 D2 equal to 0. Right? Just simplify this, or you better way multiply it by 2 everywhere. So this becomes 4D1 plus D2 equal to 28 divided by EI. Say equation 1. 28 divided by EI. So when we transfer it on right, becomes plus. Now second equilibrium condition, A22L plus K21D1 plus K22D2 equal to 0. This is 30 plus, this is EI upon 2 D1 plus EI D2 equal to 0. Right? Then multiplied by 2, this becomes D1 plus 2D2 equal to minus 60 by EI equation 2. So solve 1 by 2. If you solve in a regular way, that is also okay. Or better way, use matrix method. So this is 4, 1, 1, 2. This is D1, D2 equal to, say take 1 upon EI outside, and what is left is 28 positive and this is minus 60. Now inverse we know for 2 by 2 matrix how to calculate the inverse. So this is D1, D2 equal to, now 1 divided by determinant, it's 7 EI, and this is matrix, this is 2 minus 1 minus 1, 4, and this is 28 minus 60. 28 minus 60. And this directly, I will write down the answers. Answers will be this D1 is equal to, so you find out, this comes out to be 116 divided by 7 EI, and D2 comes out to be minus 268 divided by 7 EI. So this is nothing but theta B, this is nothing but theta C. So we have calculated theta B and theta C. Next, just apply the slope deflection equations and find out the end moment. So instead of that, so how easily from diagram itself we will calculate this, look here. So MAB, just say MAB equal to, this is anti-clockwise, minus 60, then this is plus EI upon 2 into D1 equal to, D1 we know, right? There is nothing is here. Now this is MAB, then you find out MBA. So MBA equal to, now this is plus 60. So left of B, this is plus 16. Then this is EI plus EI D1 and nothing is there equal to. Or if you want MBC equal to minus 30 plus EI D1 plus EI by 2 D2 equal to, this EI by 2 D2 equal to. So, but whatever you will get MBA, MBC and MBA are equivalent opposite. You will get same answers. So this comes out to be minus 7.71 kilonewton meter, and this is 32.57, and this is minus 32.57. So these are the answers. Now knowing these moments, now you can construct BMD very easily. And we already constructed, you just refer the BMD we have constructed in this. So you write this moment, and 7.71 and 32.57. So with these values, draw BMD, SFD. So refer our bending moment diagram we have already plotted in earlier. So today we will stop here, and a few more problems we have to solve by using this stiffness method that we will see during next lecture. Means we have to solve few more problems on continuous beams, then frames. So applications of stiffness method to continuous beams and frames. Again, we solve few more problems, and then this topic will end. So thank you very much. We will stop here.